Okay, this little added extra to the video on vertical circular motion. This is really aimed at people going for the scholarship level and trying to solve the problem of when do things go wrong. For level 3, it's probably enough to be able to work out how, whether or not the object is going to be able to safely pass around a vertical loop, but at scholarship level the expectation is probably more like working out where things go wrong when they go wrong. And so, disaster zone. It's like when the roller coaster's not going fast enough and falls off the rails, or when you're swinging that bucket of water around your head and you go too slow, the water starts spilling out. Exactly where does that happen? Just kind of thinking about the logic of the problem, we know that it's not really a problem down this bottom half of the circle. If things get too slow there, then the roller coaster or the bucket of water will tend just to oscillate back and forth in that bottom part of the circle. It's once we get above that bottom part of the circle that there's really problems. And so what we know is that we must be providing a centripetal force. Look. And the other thing we know is that the only force that really is acting is gravity, right? And suddenly things get a little bit complicated because we've got gravity going down and we've got the centripetal force kind of angling off towards the centre there. And so we're flummoxed. How do we solve this problem? And so we think back to that classic rule of vectors, that any vector can be redrawn as two other vectors at right angles to each other. We're used to doing that in projectile motion, horizontal component, vertical component. It's less usual to do it this way, but it still works. We're going to draw one component of gravity that is towards the centre of the circle, that's the one that we care about, and one component that's not towards the centre of the circle. Who cares? That's not providing a centripetal force. There we go. Two components at right angles to each other. One that is directed towards the centre of the circle. It is providing the centripetal force. And the other one that's not. And so what we're interested in is where do things go wrong? How much is that angle? And hopefully you'll believe me that this big angle here is the same as that big angle inside that triangle there. And we know the hypotenuse of the triangle is FG. We're trying to find the opposite side of the triangle, FG sine theta. And we know the limiting factor is that whenever that FG sine theta is greater than the FC, that's when things go wrong. Now, of course, some of you will have spotted this is a complex problem because as the roller coaster climbs up the loop there, that speed of the roller coaster gets slower and slower, and therefore so does the amount of centripetal force required get less and less. And so as well, we're going to have to write an equation for how much the velocity of the roller coaster might be, but that's relatively easy because it's going to be the radius of the loop, and then we can just work out how much that part of the triangle there is with the angle, with that same angle, and use conservation of energy to write an equation for how fast it's going. It's quite a complex situation, too much to solve completely on this whiteboard here. What you need to know is that tricky little step of the vector analysis. I'll be posting a problem for you to have a go at.